Question number 3. Forces on threaded ring. One end of a light inextensible string is attached to a fixed point A of a fixed vertical wire. The other end of the string is attached to a small ring B of mass 0.2 kg. Okay. And now if this mass is 0.2 kg, meaning this weight is going to be 2 newtons in this direction. Okay. Through which the wire passes, a horizontal force of 5 Newton is applied to the midpoint of the string M. The system is in equilibrium with string taut with B below A and the angles equals to 30 degrees. Okay. Show that the tension in the string is 5 newtons. Okay, so we're looking at M. Let's resolve the forces on M. There's a horizontal force towards its right, and then there's going to be a tension in this direction and a tension in this direction. Remember, we've discussed that since it's an isosceles triangle setup, the tension in both the directions would stay the same. So we've used the same variable for as we've used the same variable. We didn't use T1 and T2. Okay. That would have been the case if this were not making an isosceles triangle. Okay, so let's resolve the forces. Okay, so this is the opposite component and this would be the adjacent component because see 30 is here. So this one is going to be the sine component T sine 30 and the other one I'm drawing here. This one would be T cos 30. Okay. Now let's look at the lower triangle. Again, this one is going to be the sine component because it's opposite. So another t sine 30. So you have 2t sine 30 in this direction. And then since the arrow tension is like this, one component will be in this direction, which is t sine 30. The other one will be in this direction, but I'm going to draw it here, right here. And this is the adjacent component, meaning the cos component. So t cos 30. Okay. I think these are all the forces on M. Now equate the up force to down force. It just cancels out. T cos theta is equals to T cos theta. We're not getting anything from here. Now let's equate the left forces and the right forces. So we have 2t sine 30 equals 5. And when you divide 2 sine 30 with 5, you should get 5 newtons. So we've shown that tension in the string is 5 newtons. Okay. She says tension in the string BM is 5 Newton and it's going to be the same because it's going to be the same in this and this direction because it's an isosceles triangle being made between A, B, and M. Okay. The ring in one, the ring is on the point of sliding up the wire. Okay, now there's going to be some movement that's taking place. Okay, find the coefficient of friction between the ring and the wire. Okay, so the direction of motion has been shown by the double arrows. We have to find the coefficient of friction. The ring is about to move upwards. It's not moving at the moment. So that means up forces would be equals to the down forces. With respect to B, this is B. Tension is outwards. Okay. And let's resolve this value, this tension. This is 30 here. So we'll have a component in this direction and a component in this direction. This one is going to be T sine 30 and this one is going to be T cos 30 and there's a weight downwards and this is the direction of motion. That means there's going to be friction downwards as well. Okay, now let's equate this force to these forces. So since the system is in equilibrium, T cos 30 is equals to 2 plus mu r. Okay. Now what do we do about r? Remember, there was a tension in this direction as well. Excuse me. This was t sine 30. Let me write that here. And now, unlike the previous question, now there's a contact between the ring and the rod. And since the pull is in this direction, so the contact is going to be somewhere over here. And the normal contact force is going to be in this direction, opposite to the T sine 30 force. So there's an R in this direction. And these two forces would balance each other out. So R is equals to T sine 30. Okay, we already know from the previous part that T is 5. So replace this with 5 and replace this with 5 and get the value of mu. So we have 5 cos 30 minus 2 whole divided by 5 sine 30. That should give us the value of the normal, the mu, coefficient of friction. We get 0.932. Okay, rounded is 0.93205. I'm writing the unrounded first and then the rounding. 0.932. Part 3. A particle of mass m kg is attached to the ring. Okay, so if that's attached to the ring, so then the downward force here is not going to be just 2 Newton the weight. It's going to be 0.2 plus m times 10. The original mass was 0.2, another mass of m kgs is attached to it, and the formula for weight is mass times g, mg, and g is always 10. Okay, so this is the downward force now. Next, it says that the ring is now on the point of sliding down the wire. Okay, so now the direction of motion changes. It's now going to be downwards, which means mu r, or the friction, is now going to be upwards to on B. So let me draw B again. This is point B where the ring is. There's a downward weight, which is 0.2 plus m times 10. And then there's the same tension that we had earlier. This was T, and then we resolved it in two parts. This was T sine 30, and the upward one was T cos 30. Okay. Now mu r is in this direction and r is still in this direction. Because of this pull, r is in this direction. Okay. Now let's form equations. Okay. So the equation would be upward force T cos 30, also friction mu r is equals to downward force 0.2 plus m times 10. Okay, now friction would be equals to mu r, and I believe we have both these values now. Yep, T is also 5. So 5 cos 30 plus mu was 0.93205. R is also the same. It was T sine 30, this one, because it's opposite to R, and it's also 5 sine 30 already. Okay, and is equals to 0.2 plus m divided by 10. So you solve this, then divide the answer with 10. Then subtract 0.2 from it, and you should be able to get the value of M, which should come out to be 0.466 kgs.